Hello everyone, welcome to my talk, How to Rangify Your Code. I'm very grateful that you're spending your Saturday lunchtime with me here, learning about ranges. My name is Tina Ulbrich. I work for the ROSEN Technology and Research Center. And you may ask what qualifies me to give this talk. In my company, we use the newest C++ standards right away, which means we're among the first people who bring the new features into production code. But that also means that, especially at the beginning, there's not a lot of material available to look up how these things work. I mean, there is a lot of material available, blog posts and talks, but they tend to be very technical, and they focus on how the features were implemented into the standard library. But the examples in those talks or blog posts are usually very simple. And so this is my motivation to give this talk. I gathered lots and lots of examples, and we're going to rangify them so that you can see the actual ranges in action. And before I start my talk, I want to quickly recommend some other talks and also YouTube videos. And if you get the slide deck in the end of the talk, there will be a link to all of the talks and videos that I recommend in the slides, so you can just click on the slides then. So first, I want to recommend basically any ranges talk by Eric Niedler. You might know Eric Niedler. He is the author of the Rangify library, which was the basis for the standardization of the ranges. And in his talks, he explains in depth how ranges work and also gives examples on how to use them. Next, I have a talk from Tristan Brindle. It's called An Overview of Standard Ranges. And it's exactly that. It's an overview of everything that was or is implemented in the standard library regarding to ranges. And then I have another talk from Tristan Brindle, and it's called C++20 Ranges in Practice. And this is also, again, a very great talk. It's very practice-oriented, with also lots of great examples and background information around ranges. And if you want to learn how you can write your own range adapter, you can check out this two-piece talk from Christopher Di Bella. So range adapter is also what we call a view, and it's typically what you find on the right-hand side of the pipe operator. And Christopher shows you and shows us how to do that using C++20. And I also want to recommend Cybrand's YouTube channel. They have some live recordings on how to implement some of the range adapters like stride or transform maybe, chunk by, ranges to, and enumerate, as you can see here on the slide. And it's also very good to watch these videos and to learn how these range adapters are implemented. Next, I'm going to show you some libraries that you can use if you cannot use C++20 yet, or the standard library lacks some features for you. First, we have the Rangify library, which is the most extensive library for ranges support. And it is the basis of the range support in the standard library. And again, if you want to learn more about Rangify, then I highly recommend the talks by Eric Niedler. Then we have NanoRange, and this might be the second largest range library. It provides not only ranges, but also concepts, and the range-based algorithm, function objects, and projections, and more. And this is written in a very close way to the standard library. Then we have Cybrand's GitHub repository. It's called Tartan Llama. And they uploaded all the videos that I showed you before, all the code from the videos. They uploaded it to the GitHub. So you can get all the range adapters that I implemented from there. Then we have ranges next. This is a quite small library. It provides ranges to enumerate and product, which is a Cartesian product. But these functions are extremely useful. Sorry. And next we have boost range. And boost range supports range-based algorithms, and it already has some range adapters using the pipe syntax. So you can also check out boost range. So now that I've covered some recommendations for libraries and also talks, let's move on with the talk itself. So what do I mean when I say I want to Rangify the code? A lot of people would think of the pipe operator and what's right to the pipe operator, but there's more to Rangifying the code. But of course, in this talk, we are going to use the pipe operator a lot, so I guess you won't be disappointed. So ranges are algorithms, are loops. And we have the tendency to think in loops first, because that's what we learn first, and we're doing them the longest. So they are the most natural to us. A change in that already happened on the introduction of algorithms. It even got and still gets backlash from people saying that they are harder to read and they don't trust them because they don't see what is going on and how it is actually implemented. They like to roll their own loops, basically. And the same prejudice also holds against ranges. The syntax is the most unfamiliar, especially compared to loops. And it's way more a functional programming approach where you describe what the code does and not how the code does it. And I'm personally convinced that once you get used to the syntax, reading and writing the code will get easier and easier. The key is also to learn your algorithms and know what is available, and to analyze your code and spot the algorithm behind the loop. Ranges are kind of like a new subset of a programming language within the C++ standard. So rangifying also means using range-based algorithms. You might think there's not a huge change there. We can just omit the begin and end. But it gives you the option to better describe the intent rather than implementation details. And it also can limit the noise. And also we can now use views in these algorithms. So let's say we have a vector of doubles and we want to modify them using some kind of function. And we want to store the modified vector in another vector. We have, I think, in C++ about 1,000 ways of doing this. You can make a loop. We have while loops, we have do loops, we have for loops. And for loop, we have index-based, iterator-based, range-based, just lots of loops that you can pick from. We can also use the standard transform. This would be the C++ 17 way, where we call begin and end on the vector. And with C++ 20, now we can use the range transform function, where we don't need to call begin and end on the vector. This is very handy because usually you want to iterate over the entire range. I think this is the most common use case for transforming something. But you don't have to use transform here. You can, with C++ 20, now even use copy. If you want to make it extremely clear that you're making a copy here and storing the output in another vector, then you can use ranges copy. And you can use a transform view with the same modify function to modify all the elements in the vector, and then storing the result of that in the output vector. But to be honest, I wouldn't do any of those. I would use a feature that is not yet in the standard library, but I think it will be in C++ 23. And that feature that is missing is called ranges2. And so what I would write would look something like this. I would transform the vector using use transform, and then converting the output into a vector using ranges2. And this has the great advantage that you can now make the output const. All of these little examples tend to look a little bit over-engineered. And that's why I came up with this talk, and I collected lots and lots of examples, as you're going to see. And I try to show as many different cases as possible. So I will start with some small examples that mostly fit on one slide. So also one note to the examples, I grabbed them mostly from our code base. And I did that by just searching through the code base and searching for all the for loops. And then stripping everything, stripping the entire example from everything that would be considered company intellectual property, because I'm not allowed to share that. So the examples are also a little compressed, but in essence, this is what I found in our code. And we have a very huge code base, so there would be a lot of examples to pick from. So we're starting with finding a maximum number, and the numbers here are strings, because we grabbed some input data, and that was a string, but the string holds a number. So we have a vector of strings that represent numbers. And then we create the maximum value, which we initialize with the smallest integer value. Then we have a for loop over all the numbers. We call string to int to all the numbers and find the maximum value. And then we return the maximum. So when we want to rangify this, I first look at the loops. How do the loops look like? What do they need? Do they need an index? Something like that. So in this case, I don't need an index. And I want to transform all the strings into ints. So this is why I'm going to call, and I want to find the maximum number from all the transformed values. So this is why I'm calling ranges max, which will find the maximum value in the range that you are giving. And I call it on numbers, but I need to transform the numbers into integers. And that's where I use a transform view to call string to int again for all the numbers to get the integers. And now ranges max will find the maximum values of all the integers. So for all these examples, I highlighted the code bits that correspond to each other. So in this case, the for loop corresponds to the ranges max call, because that will iterate over all the values in the vector. Then the searching of the maximum again is done by the ranges max function. And we call a string to int. And also one note before I move on to the next example, I have some of them. If you see a Compiler Explorer symbol like here, then I have linked this example I have a link to Compiler Explorer to this example, and so you can get all the different examples and play around with them as you want to. So next we have a sliding mean. And in this case, we want to have a window of 5 elements for the sliding mean. So we will create a subrange of 5 elements in the range and move this window of 5 elements over one place, and then calculate the mean from there and move it over to one place and calculate the mean from there. And to do that, we have then, I always want to store the result in a vector in the end. So you're going to see that a lot. So to do that, I create a new vector, which is the input size -4, because we have like this window of 5 that we're moving in the input range. And then I have a for loop starting at 2 and counting up to range size -2. Again, accounting for the window size. And then I'm calling a mean function, and I create a vector in place and give the mean function all the values, all the 5 window values out of the input range. And after that, again, I return the vector. So to Rangify this, again, I look at the loop, and in this case, it might look like I need the index, but I don't actually need one, because ranges or Rangify comes with a very handy function, which is called sliding. This is sadly not implemented in C++20 yet, or in the standard yet. So I'm going to use Rangify for this example here. And what the sliding view does is basically the same as you can see in the loop above. It will create a window of 5 elements, and it will move this window over until we reach the end of the range. And this will create a subrange of 5 elements. So there will be no copies. It will just like point to the different values. And then I call transform, and I can call the same mean function as I used in the example before, because this mean function very handily takes a span, and the subrange that was created from Rangify in the sliding view can be transformed into a span. So this is very handy. I don't have to do like any conversions on that. I don't need to use any templates or something. I can just use a span in the mean function. And then again, I'm calling ranges2 to create a vector. And what I like about this example is that you can change the sliding window very easily to whatever number that you want to have. And also Rangify does all the boundary checkings for you. So the corresponding lines here are, first we have the sliding window, which is done by looping over the input range, and in the for loop, we create an array of all the 5 elements. And then we call the mean function, and then we create an output vector. So also in the ranges version, I don't need to know any sizes of the output vector. It will just work like this on its own. I think it's very handy. Moving on to the next example. We want to subtract a mean from matrix elements. And in my company, we're using Boost multi-array for the matrices. And this is a 2D multi-array, so it is a matrix. And I have a corresponding vector, which has the same amount of data as we have columns in the matrix. And it stores the mean of all these columns. And I want to subtract the mean from all the values in the matrix. So to do that, I first loop over all the rows in the matrix. Then I have a second loop, which is here an index loop, so that I can iterate over all the columns and also over the input vector. Sorry, my light just went out. Interesting. Yeah, I have a second loop, which is in this case an index loop, so that I can access the vector and the columns of the matrix. And then I do the actual calculation where I subtract the column mean from the actual element of the matrix. So when we want to Rangify this, we need to figure out what we actually want to do, what is the algorithm behind that. And what basically happens is that I want to visit every element of the matrix. And it doesn't really matter that is a matrix. I just want to visit all the elements and subtract a certain value from that element. So what I did here is I'm going to use the ranges transform. And this time not the transform view, but the range-based version of transform. And I'm going to flatten the matrix. And I do that by creating a span. And to create a span, you have different options to create a span, but in this case, I give it the pointer to the first value and the amount of elements that the matrix holds. And so span will create a view over these elements. And multi-array has like a storage underneath the structure, which stores all the values in a contiguous way. So we can actually use span here for multi-arrays. If I don't have multi-arrays, if I would have like a range of ranges, like a vector of vectors or something like that, I could also use ranges views join, which would make the 2D vector or 2D range would make it 1D. But multi-array doesn't play nicely with the join, so I cannot use that here, but this is just another way if you don't have multi-arrays and you have some kind of 2D structure that you can use. So the span is the first input value for the transform, and transform also takes a second input range if you wanted to. And the second input range in this case would be the column mean. But you might have spotted that the column mean is too short. So it only stores the column mean for one column, and it will not repeat for the entire matrix. But there's a range adapter for that as well. You can call cycle. And what cycle does is when you are at the end of the column mean vector, it will cycle back to the beginning. So it will just cycle around the entire range. But that also means that this range is like an endless range. It doesn't have a defined end. It doesn't have an end sentinel. It will be like this unreachable sentinel in the end. So that's why you have to make it the second parameter for transform, because the first parameter determines when the transform finishes. And a span has a defined end. But now that we have that, we have all the elements of the matrix flat, and all the column means that will just repeat it over and over again. I need to store it somewhere. I need to give the transform function an output place. And we use origin here again, which is a pointer to the underlying range in the matrix. And then the transform wants a function, and I created a lambda, which takes the matrix elements and the mean elements, and then it does the subtraction. So now when we light up all the corresponding code lines, we have at the beginning the nested loop, and we made the matrix flat and used transform to just flatly iterate over all the elements in the matrix. Then to get the correct column mean values, I use cycle, so that when I reach the end of my vector, I cycle back to the first element and it will just iterate again through this range. I store the output in the matrix itself, and then I do the actual calculation first in the second for loop and here in the body of the transform function. So this is it with the subject mean. I have another example. I have lots of examples. So and when you're sitting here, I hope you don't get tired of all the examples. So I have a lot of them left. Next, we have a range, and you might recognize this function from Python or something, where this is part of the NumPy package. And when you want to implement something similar in C++, so it will create a range with the size of len, starting at start and then counting up the value using the step that you gave in. So if you want to have a similar thing in C++, we again make a vector with a length of len, and I initialize all the elements with a start. Then I iterate over all the elements that I need. And in this case, I actually need the index. So for the calculation, I add I times step to the element that is already stored in the vector, which is the start. So it is start plus I times step. And then I return the vector. So to Rangify this, I look at the loop as well. And in this case, I actually need the index. And if I want an index to corresponding values of a range, I could use enumerate. But in this case, I decided that I want to have an inst view. And this is basically what iota does. It starts with the start value that you give in, which is 0 in this case, and then it ends the range with len. So we have the exact same thing that we created in the for loop, but we have a view now that that gives us the integers that we need. And then we call transform on this integer view. And we have all the values that we need already in the function. So I need start and step, and I calculate I times step plus start, and I'm returning that from the transform view. And then in the end, I create a vector. So the corresponding elements here are the for loop, the indexed for loop with the integer view, which created all the integers that we need for the calculation. And then we do the calculation once in the for loop body and then in the transform function body. And we create an output vector. So I have another example for you. I don't know what's going on with the slide. Just turns off on its own. Yeah, I have another example. So I want to sum up all the non-defective data. And in this case, I have a vector that holds a struct. And that struct basically just is a bool that tells you if the value is defective or not, and a corresponding value to that. And for the non-range-based version, I create a sum outside of the loop, which holds the result of the calculation. Then I have a loop. And in this case, I wouldn't have, I wouldn't need an indexed loop. It could have been a range-based loop. I just decided on using an indexed loop, but it doesn't matter. It could have been range-based. And then I ask every value if it's defective or not, and only add the non-defective values to the sum. And in the end, return the sum. Something different. We don't return a vector here. Yeah. So then we want to rangify this. We would again need to see the algorithm behind it. And the algorithm behind summing up values from a vector or another range is accumulate. So I'm going to call ranges accumulate here again from the Rangify library. And because the standard library doesn't have yet a ranges accumulate function. And the first element of accumulate is the range where you want to do the accumulation. But we don't want to accumulate all the values from the range. We only want to accumulate the non-defective values. And this is a little bit tricky because it would have been easier if I wanted to add all the defective values. I could just ask, I wouldn't have to negate the answer because is defective is true when it is defective. So I don't want the value if is defective is true. I want it when is defective is false. So I want to use something that you would see a lot in using ranges, or I think you would see a lot, which is a combination of filter and then transform. So I first want to filter all the non-defective values out of the range. So I only want to have the non-defective values. So I call the use filter, which is in a standard library. And I call another function, which is called not_fn. And what this function does is it negates everything from the function you give it. So if the function returns false, it will negate it and change it to true. And we need to do this in order to negate the result that we're getting from asking if it's defective or not. And we can use another very, very handy thing here that was introduced in C++ 20, which is called a projection. And a projection basically extracts a data member from an element of some class type. And it looks like a pointer to the member. So we are going to extract the field is defective from the data element that we get from the data struct, which is a bool itself. So we don't have to write a function around that, which I think is extremely handy. So is defective now returns a bool, and not_fn negates what we get from that bool, and we filter on the range on the output of this function. So if not_fn returns true, then the values are non-defective, and then we can add them. And now that we have all the non-defective values, I want to extract all the values from the data struct. And I do that by using a projection again and calling use transform. And I don't know if the lamp is too hot or something, but it doesn't feel hot, just warm. Sorry for that. Transform. Yeah, I want to extract all the values from the data struct. And I do that by using a projection again and extracting the value field from the data struct. And now the range that we have is a filtered range that only has the non-defective value, and it will have all the values, and not the data struct anymore, but only the values. And then we need to fill out the last input for accumulate, which is the start value, and we start accumulating by 0. So when I line up the corresponding fields here, the summing of all the values will be done by accumulate. The if statement becomes the filter. And then the transform extracts the value from the data struct, and accumulate itself does all the accumulation, and we start with 0. There's another way of doing this, also using ranges accumulate, where you don't have to use the transform, and I'm going to show you here. So the beginning looks the same. I call accumulate on the range, and I filter all the non-defective values. So that is all the same. But now I use all the fields that you can fill in with accumulate. So all the arguments that you can give to accumulate. So accumulate now gets the filtered range. And the next element, the next argument for accumulate is where you want to start your sum. So I want to start with 0. And then the next argument is the function that should be applied. And if you don't do anything there, it will assume you want to sum up all the values. That's why it's called accumulate. But if you want to give it another parameter, you have to specify the function, which is the plus in this case. You don't have to do anything else. You can just write plus, and the curly braces or even round braces works as well. And so that tells the function that we want to sum all the elements. And then we use a projection again to extract the value field from the data struct. Here are the two results side by side. I don't know if I prefer one over the other. I think for the first one, you might think it's strange that you call transform and then have a projection in there. But the second one, you need to know what a projection is as well. And you specify the plus function also. Yeah, so that's a little bit a matter of taste. If you like the first one or the second one better, I actually won't mind either of them. And you will also find both of the versions in the compiler explorer link. So we have another example. We are almost at the end of the small examples, and then I will move on to a bigger example. For this example, I want to calculate a length, and I have 3 vectors with coordinates x, y, and z. And the output again is, of course, stored in a vector because why not? And now I need an index loop because I want to iterate over all the elements of the vectors in sync. And I do the calculation. With C++ 11 and the algorithms, you could combine 2 ranges together in transform. So transform always accepted 2 input ranges and 1 output range. But if you wanted to combine more than 2 ranges, you couldn't use transform anymore. You would have to fall back on a vector, on a for loop. And in this case, even on an index-based for loop, which we don't actually want. But with ranges, we can use a feature that you might also know from other programming languages, like Python, for example. Python uses the exact same keyword. It's called zip. And I can make a for loop where I zip all my ranges together. And in this case, I'm going to zip together x, y, and z, and also the output range. And what zip does is it zips all the ranges together, and it returns a tuple, which holds a reference to the values in the input range, in the ranges that you give them. So since it returns a tuple of values, you can deconstruct the tuple. And this is what I typically like to do. I like to deconstruct my pairs and tuples and structs and whatnot, and using structured bindings. So this is what you see here. I'm using structured bindings to deconstruct everything that I get back from the zip tuple. And then I have a very similar calculation to the one above, but it has the advantages of a range-based for loop where you don't have to fiddle around with indices and maybe getting them wrong. And the range v3 version here of this does not do really a lot of boundary checkings. It terminates on the length of the X vector here. So if the X vector is longer, then I think it will just extend the other ranges with zeros or something. I guess I would have to look this up, but yeah, it will always run, it will always compile, but maybe you want to do some kind of boundary checking here as well, but you don't have to fiddle around with indices. But if you don't want to create a vector and then change its contents, if you want to have a const vector, then you could also make this another way. Also by using zip. So, but now we're zipping together all the input ranges and not the result. And then we're calling transform on those zipped ranges. And again, what Rangify does here is it creates another range. And this range contains tuples. And those tuples contain references to the input ranges. So there also will be no copies or anything. So now I have a range of tuples, and I'm going to iterate over all of the tuples using transform. And as I said, I like to deconstruct all my tuples, so I give them names here as well. And then I do the calculation. And again, of course, I'm going to use ranges 2 to create a vector. And again, this has the advantage of you being able to make the result const. These are the two versions side by side. The version below looks a little bit longer, but that's because we don't do everything like on the same line as we do in the result above. So both work perfectly fine, both work exactly the same. And now I'm moving to my next example. And this is the last example from the smaller ones, and then we're going to a bigger example. So this example actually looks extremely strange and kind of funny. And as I said, I got all my examples from our code base, and you have to imagine there's a lot more going on around this function and these loops. But basically, in this case, we have a vector of vectors, and the second vector contains indices, which are stored in size t. So we have a nested vector here. And now what this function is doing, it will create an output vector of size t. And then it loops over the outer vector. And then it will loop over all of the elements of the inner vector. Then it does a weird comparison where I think my lamp is not sure what's going on. Yeah, then you have a comparison where you compare the elements of the inner vector to the index of the outer loop. I cannot tell you why, but this is what I found. And then we're going to push back this index into the outer vector. And I had a little bit of a tough time rangifying this, but I also had a lot of fun. So this is why I included this example in here. I'm not sure if any of you will come across an example like that ever in real life. But as I said, I had a lot of fun doing the rangifying, so I left it in. Yeah, to rangify this, I actually now need an index. And to get an index, you can use the enumerate view. And what enumerate now does is it creates a tuple with the elements of the range you're iterating over, and it creates a corresponding index, and you get like a tuple of both of these elements. So this is what we have in the enumerate view. So now I have a tuple with the two elements, and one element is the inner vector, the entire inner vector, and the other one is the index. And now I'm transforming this range that I got. As I said, I like to deconstruct all my values here. So I get the index, which I also called I, so that it corresponds a little bit better to the loop in the loop above. And then I have the index range, which is the inner vector. And I'm going to filter that one because this is what happens in the if statement. So I'm calling ranges new filter, and this iterates over all the elements in this range and filters out all the indices that are equal to I, which is the index of the outer loop. But now what I have created is for every inner vector, I created a subrange of values. So I have a range of ranges. But as you see in the input, you don't want to have a range of ranges. You want to have like one contiguous range in the end. And to do that, we can call join. And this will join the ranges of ranges together into one big range. And then, of course, we make a vector in the end. So in my very first installment of this talk, I thought it would be good to include a disclaimer saying that just because I show you how to do stuff with ranges, you don't have to use ranges. It's just another way of doing it. And it does not mean that ranges are necessarily better. I scraped that from the first version of the talk, but I think as I included this example, it might be good to have it back again. So as crazy as the entire algorithm itself is, maybe in this case, it would have been better to not use ranges. I'm not sure how readable this would be for someone who doesn't know the code, where the above one is crazy as well, but it's more familiar to us to read those for loops because that isn't really an algorithm behind that. It's not an accumulate or a transform or something. It's like this very strange thing that is happening here. So not all examples are more readable with ranges. And of course, just because I'm using ranges, it doesn't make anything better magically. So you can decide for yourself if you would like to use ranges for that or not. And that brings us to the complex example. And this is also the last part of the talk. So we're almost finished. For the complex example, I chose a method that I want to implement first in C++ 17 and then in C++ 20 using ranges. And the method I found is the so-called HONT method. It's also called Jefferson method or the method of the greatest divisors. And it is a method of allocating seats in parliaments or proportional representation systems. And I am going to explain how it works going through this example here. We have three parties, party 1, 2, and 3. And party 1 got 110 votes, party 2 got 85 votes, and party 3 got 35 votes. And we have 7 seats to allocate. And for the algorithm, we are counting up from 1 to 7. And now we divide the votes by this integer range that we just created. So first we divide 110 by 1, which is 110, and then we divide it by 2, which is 55, and so on until we reach the 7. And we do that for party 1, 2, and 3. And now we are going to sort the results of this division in descending order. So the biggest number is from party 1, then we have party 2, party 1 again, party 2, party 1 again, and well, then party 3, and the last one goes to party 2. And now we count how many seats the party got. So party 1 got 3 seats, party 2 got also 3 seats, and party 3 got 1 seat. So this is the entire algorithm. And as I said, first I'm going to implement this with you together in C++17. And first I need to decide on the input values. I decided to use a map, and the map holds a string and an int. The string is the name of the party, and the integer is the amount of votes that the party got. And it's called votes per party. I think that's very self-explanatory. And I also need the total number of seats. This is the entire input that I need for the function. So now I need to do this calculation. I need to make an index range from 1 to number of seats, and then I need to do the division. And I also need to remember which result belongs to which party. So I decided to do this in a vector of pairs. So I want to hold the result in a vector of pairs, where the string represents the party, and the double is the result of the division. And then I have a for loop starting at 1 and counting up to number of seats plus 1 to get this index range where we want to do the division. And then I have another loop where I loop over all the elements of the map. And as I said, I like to deconstruct all my members to give them proper names. And in this case, we have the party and the number of votes, because if you iterate over a map, you get a pair, and you can deconstruct the pair using structured bindings. And then in the output vector, I'm going to push back the party and the proportional votes, so the result of the division. In production code, I would not do it like that. I would at least reserve the size of the proportional votes vector or have it a fixed size. But just to limit the noise a little bit, I removed it here. But keep in mind that if you know the size, it is not a good idea to just push back into the vector. It's not very cache friendly. Next, we need to sort the results that we got from the division. And to do that, we're again in C++17, I call standard sort. I want to sort the entire vector, and so I call begin and end. And because I want to sort a pair and also in descending order, I need to define a lambda to do the calculation. And then I'm going to resize this example to total number of seats. I'm fully aware that I can use partial sort here. I don't need to sort the entire vector, but for small input ranges, you would have to measure if partial sort is actually better or worse. So I didn't do any optimization on that code, especially not without benchmarking it first. So yeah, there are other ways to do this, but yeah, I'm just using sort here to also keep it simple. And then after the sorting, I need to count how many seats the parties got. And I count by, I first need to create an output for the function. I decided to make a map again, holding a string for the party. And now the integer represents the seats that the party got in the parliament. And I'm iterating over the input map here because I need the parties from the input. I don't need the number of votes anymore, but I deconstruct both anyways. The counting is done by calling COUNTIF on the proportional votes, which hold again the result of the division. And for the votes, the first element in the pair is the party, and I compared to the party that I get from the input map. And that's how I count all the seats that the party got. And I'm going to insert the party and also the amount of seats into the output map. And again, in the end, return the map. So this is the entire function. I changed the font size a little bit so it fits on one slide, but basically this is what you have to do. And we have 3 blocks here. We have first the calculate the proportional votes. Then we're going to sort and cut. And then we count the seats per party. And to Rangify this entire algorithm, I'm going to go through all of these blocks one by one. And I'm going to use Rangify here because I'm using some functions that are not implemented in the standard library. So we start with the first block, which is calculating those proportional votes and doing the division. And again, I think the hardest part of transforming code like this is to know what algorithms you have and also the algorithms behind what you're seeing here. But I guess that's probably true for all new skills. So what we have here is a for loop. Starting at 1 to total number of seats plus 1. And I'm going to do something very similar that I did for a range. I'm going to make an integer view, starting at 1 and counting up to total number of seats plus 1. And this last element for views is exclusive as well. And now what I want to do is to combine all the elements of one range with all the elements of another range. And the first range here would be the integer view, and the second range would be the map. So I want to combine all the elements from the integer view with all the elements of the map. And there is a function for that. It's called Cartesian product. Which I think might be a little bit confusing because when I first heard about this, I thought there's some kind of multiplication going on there, but it's just a combination that is going on. And I'm going to show you what Cartesian product gives us as a result. So it, as I said, it combines all elements of one range with all the elements of another range. So the first range here is the map. And the first element of the map is this pair that you see here. It's party 1 and 110, which is the number of votes that the party got. And the second range is the integer range. And the first element of the integer range is 1. So the next 2 elements would be the next element of the map, and then again, the first element of the integer range, and then the third element of the map, and the first element of the input range. And now we are counting up the elements in the input range, and so on and so on. So we will create a huge range where every value of the one range is combined with every value of the other range. And as you can see, every element of this combined range is a pair. So we need to have that in mind, because we are going to call transform again. And I wrote a function which is called divide votes by seat divisors. And this function looks something like that. It's a lambda. And votes and divisor, which is the argument of the lambda. Again, it is a pair. This is what we saw in the beginning or in the slide before. So this is a pair. And a pair can be deconstructed. So I deconstructed in party and vote, which is again a pair, but this time it is a pair from the map. And then I have the divisor as the second element of the pair. And then I'm going to return a new type. I decided to not use a pair anymore. I'm going to show you with the sorting why. So I created a struct which holds the party as the first element of the struct and which holds the result of the division as the second element. And I'm going to do this calculation here and return this new struct that I came up with, which now holds the party and the quotient. And of course, I create a vector. So in this case, again, the outer loop with the index corresponds to the integer view. And then the nested loop corresponds to Cartesian product, where we combine all the ranges together. And then we do the calculation itself. It looks a little bit more in the C++20 code because I extracted the calculation into a named lambda. But I think it has some advantages if you do that. So you can hide the implementation of the lambda like somewhere else. And if you give it a good name, it actually should be readable without you knowing the contents of the lambda. And again, ranges2 creates a new vector, and we did that manually for the C++17 method. Next, we need to do the sorting. And we can now use the ranges sort. We can use standard sort here again. We put in the entire range. And we also need to specify the how we want to sort. So I just did the exact same thing as I had in the C++17 version. And then I do the resize. But as you might remember, I just said I don't store the values in a pair anymore. I gave it, I made a struct and gave it names. So I now can say I want to compare proportion to proportion, which is quite handy that I have a struct now, because I can now use a protection again, and I can extract the proportion part from the struct. Funny enough, I could actually do that for pair as well, because pair has member function, member fields that are called first and second. But it looks very strange. It would be like std pair of string int and then first and second. So it would work, but it would look very strange. That's why I gave it a name here. And now you don't have to look into the lambda to know how we want to sort. We can just now call std greater, and then you see you want to sort in descending order. So I think that alone makes it extremely readable. If you're using Rangify, then you can also use a so-called action, which is called action in Rangify. And this does the same thing. It's actions sort in this case, and you first define how you want to sort, and then you can also give a protection. So it looks very similar to the standard version here, but the ranges sort has this pipe equals operator where it applies the sorting directly to the vector on the left side of the pipe equals, which I think also looks very nice. And for now, we're going to omit the resize, and I'm going to show you later what I did with that. And the last part is the, I guess, the most complicated part, also to Rangify. And it is counting how many seats the party got. As you can see in the loop above, we only really need the party of this vector. So we only really need the keys. And we can do that with ranges. We can only get the keys. We could also only get the values, but in this case, I only want the keys. And the keys now are the names of the parties. So it's always important to know what you're getting out of the views. So in this case, we get now all the names of the parties. And then we're going to call transform. I made a function here to call in the transform because it would be way too big. It's called count seats per party and takes the proportional votes and the total number of seats. And I hope the name is clear enough that you could read count seats per party and you know what the function is doing without actually having to look up the function itself. And then I use ranges tool to not create a vector, but to create a map, which works perfectly well, perfectly fine as well. But it's also a ranges tool call. But now I need to show you how I implemented the count seats per party function. And keep in mind that we're transforming on the keys of the input map. So we're transforming on the names of the parties. And we have those two other inputs that we need. And we're going to return a lambda so that we can call this lambda from the transform function. And again, this lambda now gets all the party names. So this is what you see here. And now I want to calculate the number of seats, which is another function that I'm going to call here. I'm showing you in a second. And I'm returning a pair with the party name and the number of seats. And this pair will be used to construct the map in the ranges2 function. So the last thing we have to do is to calculate the number of seats. And this is again another function. And I'm going to use COUNTIF as I did in the C++17 version as well. And now I don't count the entire range, but I use the take view to only take the total number of seats. And this replaces the resizing of the vector. Resizing is actually not a problem in this case because we're shrinking the vector, but you could also use it just like that. And I want to showcase a lot of different view adapters. And so I'm going to show you take here, which only takes the amount of elements that you want to have without manipulating the range. So if the range would be const, for example, you wouldn't be able to do a resize. And now this proportional votes again is a struct. And this struct holds the party names and the proportional votes, but we already sorted that. And now I want to compare the party from the proportional votes to the party of the input map, which is what I'm doing here. And this is calculating the number of seats. And if I don't give you all the helper functions that I wrote, this is the pont method in C++20 using ranges. And I hope if you read it like that, you know what is going on without having to look up the implementation details of the ranges adapters itself and also of the functions that I wrote. So I hope this is clear. If you want to, again, play around with the examples yourself, we can then go over to Compiler Explorer and play around with them a little bit. But this is the final result that I came up with. And this brings us almost to the end of the talk. The last time I did this talk, I got the question of, well, how's the performance? So I got another chapter, which is called performance. I wanted to use QuickBench to measure the performance, but QuickBench only has an old version of Rangify, and it doesn't support ranges 2, for example, which I used extensively throughout the entire code. So I couldn't use QuickBench, but I used Google Benchmark. And before benchmarking, I did a teeny tiny improvement in the C++17 code because I told you that I would reserve at least the size of the vector and not just pushing back all the elements on the fly. So I did that before actually measuring the performance. But this is the only change that I did to the code. And then I had 3 sets of inputs, a small one, which is the input shown on the slide. So we have 3 parties, 7 seats. Then I have a medium-sized input, which is 15 parties and 700 seats. And then I have a huge input, which is 60 parties and 7,000 seats. And you can see the combination of those is extremely high. So if you don't want to read the numbers, I made some charts. For the small input, the C++20 version was a little bit slower. Please note that we have nanoseconds here, and now we're moving on to the medium input, and now we have microseconds, and now the C++20 method is faster. And for the huge input, C++20 is also faster, but you can see in all of these examples, it doesn't really make a difference. All of the numbers are quite close to each other. And again, I have to say, I didn't do an in-depth analysis of the 2 solutions and trying to optimize both of them. I mostly took them as they are. And I know that there are some potential for improvements in both of them, but I might leave it to the next version of this talk to explore those. And also, please keep in mind that we are comparing here the performance of the standard library to the performance of Rangify, because I used Rangify throughout the C++20 code here. So those numbers won't really help you to find out the performance of the standard ranges. If you are interested in that, please let me know. I will try to do my best to implement the missing functions as closely to the standard as possible, or as closely as the standard will implement them. And then I'm going to measure performance again, so that we get more accurate numbers of actually the standard library and not the Rangify library. And yeah, this brings me to the end. Short summary. There are tons of great talks out there about ranges, and they vary from how ranges work to how you write your own range adapter to what is available in the standard library. Also, there are many libraries for you to use. The most complete one is the Rangify library. And not every range-based code uses the pipe syntax. It's also the range-based algorithms. And the key to Rangify the code is to know the algorithm behind what you're having, and also to know what is available to you in the libraries. Yeah, if you get used to this way of thinking, it will get easier over time. I had a hard time Rangifying the results in the beginning, and then in the end, it really got easier and easier. Performance-wise, it could go both ways. So if performance is an issue for you, like always, you would have to benchmark. And yeah, so on a last note, what we do in my company is we use a combination of the standard ranges and self-written range adapters. Since the standard ranges still lack a lot of features that we want to use, but it provides a framework for you to write your own views. We are free to use ranges in new code and also change existing code to ranges. So I hope this motivates you to do the same in your company.